Hello, advanced geometry students. It's Mr. Donaldson here, and today we're going to talk about section 7.3, which is compositions of transformations. So what that means is that you essentially apply one transformation to a figure, and then you apply another transformation to its image. The resulting transformation is what we call a composition of transformations. So let's take a look at an example of this. All right. So triangle ABC with vertices at A is at negative 8, 6. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6. Oops, almost made it. Hang tight. A is at negative 8, 6. B is at negative 5, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And C is at negative 7, 1. Negative 7, 1. All right, so there's my triangle. And what we're going to do is we're going to just follow the directions here. And it's first translated by this ordered pair rule. That's obviously a translation, and it's telling me to move all the ordered pairs right 5 and down 3. So I'm going to do that to all of them. So I'll change colors here. And this will be the primes. So if I move everything to the right 5, 1, 2, 3, 4, 5, and down 3, 1, 2, 3. This would be A prime. If I move B, right, 1, 2, 3, 4, 5, and down 3, 1, 2, 3. This is B prime. And then if I take C and move it 5, 1, 2, 3, 4, 5, and down 3, 1, 2, 3. This is C prime. And then I'll connect the dots there again, and we have a triangle. Of course, this is a rigid transformation, so that image is congruent to the pre-image, even though my drawing is not the finest I've ever seen. All right, then the next step is we're going to repeat that process. And this time, we're going to take triangle A prime, B prime, C prime, and we're going to translate it by this rule. And this rule is telling me to move everything to the right 6 and up 1. So I'll do that. 1, 2, 3, 4, 5, 6, and up 1. That's A prime, prime, or A double prime. B, 1, 2, 3, 4, 5, 6, and up 1. That's B double prime. And then C, 1, 2, 3, 4, 5, 6, and up 1. C double prime. And then I'll connect the dots. Bam. And that, my friends, is a composition of translations. So we perform the translations on the graph. Bam. What single translation is equivalent to the composition of these two? So the idea is to think, hey, instead of having to do 2 moves, how could I do that in a single move? And you'll notice that combined, I moved first everything to the right 5, and then I moved everything to the right 6. So that is the same thing as moving everything right 11. And then in terms of the y coordinates and the up and down, I went up 1, and then I went down 3. So, or excuse me, vice versa. I went down 3 first, and then I went up 1, which that gives me a total movement of down 2. So instead of doing those 2 moves, I could have gone directly from the red triangle, or triangle ABC, to the green triangle, or triangle A double prime, B double prime, C double prime, if I followed this simple rule. X comma Y, and then I draw my little arrow. This time, I could do it all in one foul move if I went right 11, and then Y down 2. For a translation vector, so that's a word pair rule, for that translation vector, it will be 11, comma, negative 2. That's it. Pretty straightforward. It's just kind of saving you that middle step. And that's what a composition of translations is. So really, the shortcut there simply is to compose translations. All you got to do is add up the X translations, which is what I did. The 6 and the 5 gave me 11. And the Y translations, the positive 1 and the negative 3 gave me negative 2. And that will give you the translation vector, or the new ordered pair rule. So for just kind of a quick, short example, find the translation vector for this composition. You'll notice that I got plus 5 and minus 2. Well, that would be a total positive movement of 3. And then for this one, I got y minus 3 and y minus 4, which is a total movement on the y's in negative 7. Simply add them together, and then you get your single translation vector that represents that composition of translations. All right, the next thing we'll talk about is a composition of rotations. Pretty simple and straightforward. Most important thing is to keep in mind that direction, okay? So name the single rotation that can replace a composition of 180 degrees clockwise and 30 degrees counterclockwise. let me draw you a quick little sketch of what that looks like. This will be really easy. So let's say we're going to rotate around this point here, and I've got point A. So first thing I'm going to do is I'm going to rotate 180 degrees clockwise. So that will put A prime right here. That was 180 degrees. And then the next thing is to do 30 degrees counterclockwise. So this time I'm going to go backwards 30 degrees. And that will make that a double prime. So how could I have done that in one move? Well, I could have either, there's two choices really. I could go clockwise 150 degrees. Or I could have gone counterclockwise 210 degrees. Either one of those would give you the single rotation that would satisfy that composition of rotations. So really I could give you two answers here. It could be 150 degrees clockwise or 210 degrees counterclockwise. You simply just add if it's the same direction or subtract if they're different directions. It's as simple as that. All right. So next is what's called composition of reflection. So we're going to do two little activities here. I'm going to use my little nerd program, the Geometry Sketchpad, to demonstrate this for you. All right. So let me go to the nerd program. And the first thing we're going to do is we're going to do a composition of reflections across parallel lines. So the first step is I'm going to reflect this concave, what is that, a quadrilateral? I'm going to reflect that concave quadrilateral over line 1. You'll see it gets reflected. Boom. Now I've got that image. And this point, by the way, is D. And when I reflected it, it became D prime. The next thing I'm going to do is I'm going to take the image, this lighter blue concave quadrilateral, and I'm going to reflect it over the second line that was parallel to the original. And when I've got there, this is the green one, and it is the result of doing a reflection over to the first line and then reflecting that image over the second line. And you notice down here the bottom point there is D double prime. So what is that equivalent to? You'll notice that that is equivalent to a single translation. So when you reflect over parallel lines, it's exactly the same thing as simply sliding that object or a translation. And the next thing is the distance of that translation vector. And the easiest way for me to demonstrate that is to just kind of screen grab this thing and show you over here. So when we have a reflection, we know that this distance from the original point to the first line of reflection is the same as from that line of reflection to D prime. So these two are equivalent to one another. Also, by the same logic, this segment is equivalent to this segment. And so what we know, or tell simply, is that suppose that this was like 5 inches and this was 3 inches. Well, the distance between those two lines would be 8 inches. And now notice the distance of that translation. Well, if this is congruent to this, then this is 5 inches. And if this is congruent to this is 3 inches. And notice the distance of that translation from here all the way across is 10 plus 6, 16 inches. And what you should notice is that distance of translation is double the distance between those two lines. And that's what we're going to add to our notes. All right, so as we just discovered, oh, and you all, where it says to draw a rough sketch, what I'd like for you to draw is exactly what I just had here, this sketch from the previous screen in the slide. So you could pause and you can draw that little sketch. A composition of two reflections across two parallel lines is equivalent to a single translation. In addition, the distance of the single translation is equal to double or twice the distance between the parallel lines. And again, you have that example. Hopefully, you draw that sketch on the space provided in your notes. All right, so the next is, what if we do a composition of reflections across intersecting lines? And so it'll be a kind of a similar idea. Let me pull up my little nerd program here. Take a look. So first, we've got this concave quadrilateral again. All right, we got point D here. And we're going to reflect it over the first line. Notice these lines, the line 1 and line 2, are intersecting this time as opposed to parallel in the previous example. We'll reflect it. And there you have the image, and you notice that's D prime. And then we're going to reflect that image over line 2. Get that reflection again, and that's D double prime. And what you'll notice here, it's almost like a tomahawk chop kind of a deal. That's equivalent to a single rotation. And we'll talk about what we know about that rotation right now. And then this is what you can draw on your notes in the provided space. So here's what I know based on the reflection. I know that this angle is equivalent to this angle because of that reflection. And I know that this angle is equivalent to that angle because of that reflection. So suppose this is 20 degrees and this is 10 degrees. So the angle between those two lines is 30 degrees. Here's the angle between those two lines of reflection. Is 30 degrees. And then this angle would also be 20 degrees. And this angle would also be 10 degrees. So now, what's that angle of rotation? Well, that angle of rotation from D all the way to D double prime is 20 plus 20 plus 10 plus 10, which gives me 60 degrees. And so what we notice is that the angle between the lines was 30 degrees, and the angle of the entire rotation was double that, 60 degrees. And you can draw that little sketch right there in the space provided in your notes, and then we'll fill it in. So a composition of two reflections across a pair of intersecting lines is equivalent to a single rotation. The angle of rotation is twice the measure of the acute angle formed between a pair of intersecting reflection lines. Same idea, just a rotation instead of a translation. All right, and then the last thing here on today's notes is what's called a glide reflection. A glide reflection is simply a combination of both a translation and a reflection. So you notice, when we start off with this foot, so here's the original foot here. If you reflected it, it would be here. But then you also translated it, so that gives you the second foot is here. That's called a glide reflection because you're doing two things. You're translating, like gliding or sliding, and reflecting, alternating. So this example of the footprint is a glide reflection, and also this example of the leaf is a glide reflection. Because this leaf, if it was reflected, would be here. Well, let's see if I can draw a better leaf. That's pretty good. And if I were then going to translate it, it would end up right here where it is. So that's it. Simple concept. Glide reflection, you do both a translation and a reflection. It's a composition of those. All right, well, thank you all. That's the notes for 7.3. Let us know if you have any questions.